Another view, which I will call the prior view, uses a bit more of Bayesian reasoning. So let's take the noise case, and let's say that we have a linear function. Okay, so our function is linear. It's just the x's that we have times some coefficients. And you might say, wait a minute, maybe it doesn't capture all the structure of the data. I mean, a linear structure is just a line, or in higher dimension, it's a plane or a hyperplane. But as you saw in the data that I gave you here, it doesn't look like a line, a straight line. It looks like some sinus function. It looks like something that doesn't fit a linear model. And to this, I tell you, okay, wait, we will fix this in the next few steps. But for now, let's just assume a linear model. Okay, so what will be the likelihood of our model? Assuming that we have some noise term, epsilon. Okay, so now y distributes normal x transpose w with sigma square. And if we want to know the likelihood of our data, we just take the product of all of our PDF points, which will be this thing over here. And we can see that the likelihood is basically multivariate normal with x times w, where x is now an n by p matrix, yeah, which each row is a new observation, and the observation has p denotes the number of dimensions of x. So in our case, it would be 1, but it could be also more than that. Okay, and now what we will do is we will assume some prior on our weights. Okay, we will assume that our weights come also from a normal distribution. So our weights, it's a p by 1 vector. And we assume it comes from multivariate normal distribution with some prior covariance matrix, which I will denote as big sigma p. Okay, so if we have this, then what will be our posterior? What will be our weights given our data? Well, it will be proportional to the likelihood times the prior. And after a lot of derivation, you get that this is actually also multivariate normal with some mean vector m and some covariance matrix a minus 1. Okay, and the way to derive this, it's the same trick in all Bayesian calculation. You just ignore everything which is not related to w. Okay, you throw them out because it's proportional to, and you will complete the square, and you will just get that this result. Okay, and what is m? M is just this thing over here, and a is this matrix over here. Okay, which is p times p in dimensions. Okay, so now we have that. This was the, again, the posterior. But we want to predict new values, right? So if we give new values, then the new values will be just x, and we denote the new value as x star transpose times this weight vector. Okay, how will this distribute? Well, it's just we are multiplying by a vector or a matrix. So by the laws of multivariate normal, it's just the dot product with the mean, and for the variance we have to do it from both sides. Okay, so this will be for a single observation. For a matrix of new observation, it will just be this thing over here. And yeah, we can stop here. Okay, this is our solution. We can plot this vector. This will be our mean function. We can have for each point confidence interval, and we are done. But as we mentioned before, linear function might be too limited. So one solution is to project to a high dimensional feature space, which is usually denoted by phi of x. Okay, and an example of this could be, for example, a polynomial basis function, which is 1, x squared, etc. Okay, so the only thing that changes is now that instead of x's, we have the phi of x's. Okay, everything else in the derivation will be exactly the same. So the only thing we change is we moved from this equation to this equation over here. Now, as I mentioned before, a is p times p. We need to invert it in our calculation. Yeah, both the mean and the variance require that we invert this matrix. And if our p's is smaller than our n's, then it's okay, we just do it. But it might be hard to do it if our p's are very big, especially if they go to infinity. And why would they go to infinity? Well, for example, the squared exponential kernel that we saw before, also called radial basis function, it's the same as having a basis function, a high dimensional feature space phi of x, that is infinitely long. And why is that? Well, to do this, you use the expansion, the Taylor expansion of e to the power of x. And I will also post a link in the description that shows this part. It's also very common to see this in support vector machines. Yeah. Okay, so what are we doing? We said that A might be infinite by infinite long. So it's a problem. We need to find something else, some other representation that we can actually calculate. Okay, so let's define a kernel matrix, or NK, as x times the sigma p times x transpose, and we'll define this to be k. Okay, and you can see that this is n times p, p times p, p times n. So this is all thing is n times n. So now let's look at this expression. Okay, if we look at this expression and we open the k, we get this expression over here. And I say that this is equal to a times this thing over here. And you can just check this. Just take a, the expression for a here, and multiply it by this expression, and you see that you will get this expression over here. Okay, now I want to multiply from the left side by the inverse of a, and multiply the right side by the inverse of this matrix over here. Okay, so this is what I do. I took this equation, a minus 1 on the left, this thing on the right. Okay, what do we get? Here the a minus 1 and a cancels, so we are just left with this term over here, and here is this cancels, so we are only left with this thing over here. Now we want to look at the mean. Yeah, we want to calculate the mean of our new points. Okay, so what are the mean? It's just this thing over here. What is m? Well, it's just this expression over here as we defined it before. Okay, but now I want to take this part and replace it with this part over here, because I just showed you this identity here. Okay, and we get this whole expression over here. And now I will define this thing to be kx star x. And what we get kx star x times kxx plus sigma squared I, all this inverse, times y. So we see that we actually got the same form as we had before for the mean. Only now, the matrix that we have to invert, this thing over here, is only n by n. It's not p by p. And again, if p is infinite, then we cannot invert an infinite matrix. But if we transform it into this form, it's just n by n, and this we can already invert. Okay, and if we do the same thing for the variance, you will get that the variance is also equal to the same expression as before. And to do this, you have to use the matrix inversion lemma. I won't show the algebra here, but basically you have to use this formula over here, which also appears in the Rasmussen book, which I will leave a link in the description. So, and this was derivation work for x, but you can do it exactly the same if you move to a higher dimensional space by replacing it with phi of x. And the derivation stays exactly the same. So the K matrix, instead of, as we defined it, to be x times sigma p xt, it will be phi of x sigma p times phi x transpose. Okay, so this was the second view, the prior view, which also uses the projection to higher space.